Hi, everybody. It's Professor Mitchell. Welcome to Math C, Intermediate Algebra. Looking forward to spending this term with you. Math C holds a special place in my heart. It's probably a course that I know inside, outside, frontwards, backwards, more than any other course I teach. I've taught it many, many times, including quite a few times online, but what's different this semester is that I have decided to record my own videos instead of using the ones from the publisher. So I hope you enjoy these videos and get a lot out of them. I did make these PowerPoints myself. That's something else that's different. Even in other courses where I've recorded my own videos, I tend to use the publisher's PowerPoint. So let's get started. Math C starts with chapter 6 in the textbook Beginning and Intermediate Algebra by Elaine Martin Gay. So chapter 6 is about factoring polynomials. So in the first section, 6.1, we're going to talk about the greatest common factor and factoring by grouping. The objectives in this section are to find the greatest common factor of a list of integers, and then find the greatest common factor of a list of terms. Next, we will factor out the greatest common factor from a polynomial, and we'll end this section by looking at factoring by grouping. And this goes with the course student learning objective, which is to rewrite polynomials in factored form in order to simplify expressions and solve equations. All right, so what do we mean when we talk about factoring a polynomial? Factoring a polynomial means to write the polynomial as the product, meaning multiplication, of smaller polynomials. So hopefully in other math courses, you've talked about factoring integers or factoring whole numbers. So if I were to ask you to factor the number 15, that means I want you to write it as 3 times 5. 3 and 5 are both prime numbers, meaning they can't be broken down any further. We also have something called prime polynomials. So these are polynomials that can't be broken down any further. So that's what we're trying to do with our polynomials, is break them all the way down into the product of polynomials that cannot be broken down any further. And when we've done that, we say that we have factored the polynomial completely. So it is the reverse of multiplying polynomials in chapter 5 of this book. And something else that's new that I'm doing this semester that I hope is helpful is that I've assigned a quiz at the very beginning of the semester that goes over all of the material that I expect you already know. And the last few questions in that quiz talk about different ways of multiplying polynomials together. So this is now the reverse of that process. All right, so starting with the greatest common factor, first let's review finding the greatest common factor of a list of integers. And my favorite method for doing this is prime factoring. So here's how that goes. Step 1 is we will find the prime factorization of each number using a factor tree, for example. Then we will write these prime factorizations in columns. And I'll show you exactly what I mean when we get into the examples. Once we have those prime factorizations written in columns, we will circle the smallest power in each complete column. And again, you'll see exactly what I mean when we do it. The product of those circled factors is the greatest common factor. So let me get my tablet ready to go here. That's where I'm going to do my examples. So when I'm teaching this course face-to-face, usually the way I do it is I bring the examples up one at a time and then do them at the whiteboard. This is going to be just a little different. So you see the examples here. These are the 4 examples that I'm going to go over for finding the greatest common factor of a list, either a list of numbers or a list of terms. And then I will switch over to my tablet and we'll do them one by one. And you'll see at the top of each page on my tablet, I have written that example down again. So you don't have to worry about scrambling to write it down now before I switch over. A couple of other things I want to point out nice and early. Number one, remember this is a video, all right? So you can pause it anytime. If you decide that the video is too long to watch all in one sitting, well, you can break it up as much as you want to. Another thing I like to encourage you to do is if you feel like you might already know how to do the next example, pause the video and try it, and then come back and compare notes with me. All right, so I'm going to switch over to my tablet. And let's see. No, wait a minute. Okay. Having a little bit of an issue here. My mouse pointer seems to have disappeared. Okay, I think okay. It's working. All right, so this is part A of the find the greatest common factor example. So here's how I do that. I'm going to take each of these numbers and find their prime factorization. So for 10, that's just 2 times 5. And since 2 and 5 are both prime numbers, I'm going to circle them. I'm done with 10. 15, I'm going to do the same thing. 15 is 3 times 5. Now 40, I have a few different choices how to break up 40 because it ends in a 0. I'm usually tempted to use 10 as one of my factors. 10 and 4 are not prime numbers. They can both be broken down more. 10 is 2 times 5, and 4 is 2 times 2. Okay, so here's what I mean by write the prime factorizations in columns. Starting with the 10, I'm going to write 2 times 5. So I've got a 2 column and a 5 column. 15 is 3 times 5. 3 is a different prime factor. It needs its own column. So I'm going to put the 5 underneath the other 5, but then I'm going to put the 3 over here. So, so far I have 3 different prime factors. I have 2, 5, and 3. Now the 40 broke down into 2 times 5 times 2 times 2. I'm going to write that 2 as 2 to the 3rd, and I'm going to put it under the other 2. And then the 5 will go under the other 5s. All right, so remember on the list of steps, it said circle the smallest power in each complete column. A complete column is a column where there are no numbers missing. So for example, I don't have a 2 in this column, so that means this column is not complete. And I don't have a 3 either here or here, so that is not a complete column. The only complete column for these prime factorizations is the 5 column. And when I go to circle the smallest power, it's actually a tie. All right. So you can just pick any one of them. And the greatest common factor of these 3 numbers is 5, which you might have been able to tell just by looking. But the great thing about this method is it works even when you have bigger, more complicated numbers, like in the next example, I think. So let's look at that. We'll go to the next slide. So this would be a good time maybe to try to work ahead of me a little bit if you're feeling frisky. All right, just pause the video at any time. And when you're ready to compare notes, come on back. All right, so 28, you could write that as 7 times 4. And then 4 you can write as 2 times 2, and I'm done with that one. So that's 7 times 2 times 2. 70, I'll write that as 10 times 7. 7 is prime, but 10 goes 2 times 5. And then 126, I got to think about this one a little bit. So one of the classes that I teach is Math 20A. which is a class for people who want to be teachers. You might be taking that class next after this one. And if you are, it's likely I'll see you there. I teach that course online very frequently. So one of the things we go over in that class is called tests for divisibility. And as an example, I know that the number 126 is divisible by 9. And how do I know that? Because the digits 1, 2, and 6 add up to 9, which is divisible by 9. Okay, now the other thing I'll point out is please, please, please feel free to use your calculator to figure out any of these numbers. So for example, I could use my calculator to figure out what is 126 divided by 9. It is 14. And of course, 9 goes 3 times 3. And 14 is 2 times 7. One of my favorite sayings is don't be a hero, hashtag DBAH. And what I mean by that is if there's something that you can easily figure out on your calculator, I would rather you use your calculator and get it right than try to do it in your head and get it wrong. All right, don't be a hero. Okay, so now let's write these in columns. We have 28 is 2 to the second times 7. 70 is 2 times 7, and then I got to put the 5 over here. And then 126, let's see, is 2 times 3 squared times 7. So 3 squared goes all the way over here. I have a total of 4 columns of prime numbers, 2 of which are complete. This one is not complete, this one is not complete, but in the 2 column, the smallest power is 2. It's a tie between these two. So just pick either one. And then in the 7 column, I have a 3-way tie. Just pick any one of those. And the GCF is the product of those circled factors. 2 times 7 is 14. Whoops. There we go. All right. So that pretty much takes care of GCF of a list of numbers. So now let's start looking at terms. This is one of those situations, and believe it or not, there are situations like this, where the variables are easier than the numbers. And the reason I say that is because expressions like p to the 9th and times q to the 8th and p to the 11th times q to the 2nd and p to the 5th times q to the 4th are pretty much already factored. All right, I don't have to do the factor tree part. I've got my p column, I've got my q column. All I have to do now is grab the smallest power in each complete column. These are both complete columns, so I'm going to grab p to the 5th, I'm going to grab q to the 2nd, and the GCF for this list is p to the 5th times q to the 2nd. That was the fastest example so far. Okay. All right, so for the last example of this type, I have thrown the numbers and the variables together. So the first thing I'm going to do is do factor trees on the numbers. So 50 is 10 times 5, 10 is 2 times 5, 63 is 7 times 9, 9 is 3 times 3. Okay. So the first step for finding the GCF for this pair of terms could be to find the GCF for 50 and 63. Now, I thought it was important to show you an example like this. 50 is 2 times 5 squared, but notice 63 does not have 2 or 5 as a prime factor. It has 7 and 3 to the second. So this list has no complete columns. And whenever that happens, it means that the greatest common factor is 1. 1 is always a common factor because 1 is a factor of everything, right? It's a factor of every number and every variable. It's just not always the greatest common factor, okay? But sometimes it is the greatest common factor. So now I'm going to look at the variables. We'll just put those in columns. I think we are going to get something out of those. So we have x to the 5th, y to the 2nd, z, and then we have x to the 9th times z. So notice that the y column is not complete. However, in the x column, the smallest power is x to the 5th. And in the z column, it's a tie between z and z, so I'll pick z. The GCF for the variables is x to the 5th times z, which means, and I'm sorry, I didn't mean to, let's get rid of the circle because that's not the final answer, and I accidentally just erased. Okay, kind of made it look like the final answer, but the final answer really is here. This fancy symbol means therefore. The greatest common factor for the whole problem is 1 times x to the 5th times z, which of course can just be written as x to the 5th times z. All right, there we go. So that takes care of finding the greatest common factor of a list of either numbers or terms. So now we'll go back to the PowerPoint and see what other kinds of problems we have to do here. Okay, so next we have factoring out the GCF. Throughout the course of this chapter, you're going to learn what I call a bag of tricks for factoring polynomials. The first trick you should always try is factoring out the GCF. Certain factoring problems become much harder or even impossible if you don't look for the GCF first. So throughout this chapter, I'm going to remind you over and over, look for the GCF first. Okay. All right, so here we have a whole bunch of examples of factoring out the GCF. So factoring out the GCF, I think of it as being in 2 parts. First, we have to find the GCF for the terms in the polynomial. And then we have to write the polynomial as that greatest common factor times another factor. So I'll show you the way that I like to think about that. All right, so again, 5 examples. I'm going to switch back to the tablet. I've got these all written down already. Okay, starting with 42x minus 7. So since we've already gone over finding greatest common factor, I'm going to do that part a little faster. One nice thing about a video is that whenever I say something that doesn't make sense, you can pause the video and think about it, or go to the discussion boards or email me. Of course, if we were in a classroom together, you could just stop me and ask me. That's another good tip, by the way. As you're taking notes on these examples, if there's anything that doesn't make sense, write yourself a little question in the margin of your notes, and then you could ask me about it later. Okay, so the GCF for these 2 terms is 7. Okay, so that's something that I would encourage you to pause the video and think about. Why is it 7? Okay, now I have my own special Mitchell way of explaining the next step. I call the next step a thought bubble, like you see in comic strips. And what happens inside the thought bubble is I want you to think about what happens when you take 42x minus 7 and you divide each term by 7, because that's going to tell us what our other factor is. All right, so if you divide those two terms by 7, you're left with 6x minus 1. And what we're looking at now are the two factors of our polynomial. So what this means is that 42x minus 7 factors into 7, which is the GCF, times 6x minus 1, and that is your final answer. So that's exactly how you're going to write your answer when it says factor out the GCF. All right, next, kind of similar example. Notice that this one starts with a minus sign. So what's often a good idea in any polynomial where the leading term or the leading coefficient is negative is to include the negative sign with your GCF. So I'm going to say that the GCF for this polynomial is negative, and then the GCF of 6, 9, and 3 is 3. And the GCF of a to the 4th, a to the 3rd, and a to the 2nd is a to the 2nd. All right, now I'm going to do thought bubble. And what I'm going to think about in the thought bubble is what am I left with after I divide each term of negative 6a to the 4th plus 9a to the 3rd minus 3a squared by negative 3a squared. All right, so how about it? Negative 6 divided by negative 3 is 2. Excuse me. A to the 4th divided by a squared is a squared. 9 divided by negative 3 is negative 3. A to the 3rd divided by a squared is a. And then negative 3a squared divided by negative 3a squared is plus 1. What I would like to point out to you right now is notice what happened to the signs of the terms. So I started off with negative, positive, negative. And after I factor out a negative, I have positive, negative, positive. It switched the signs of each and every term. So that's a good thing to remember for when you're factoring out a negative. So now I'm ready to write my answer. Negative 6a to the 4th plus 9a to the 3rd minus 3a squared factors into negative 3a squared times 2a squared minus 3a plus 1. Another thing I'd like to point out, and I'm not going to spend a whole lot of time on this in this section, factoring problems can get kind of complicated, but the good news is that they are always very easy to check. And the way that you check them is by multiplying the polynomials back together. So I think the answer is this, but if you wanted to double check, you could just distribute that negative 3a squared back into the other polynomial, and you should get your original problem back. Okay? You'll see me doing that more in later sections. Okay, moving on to letter C. So I know the fractions tend to scare some people. This is not too bad. So let's see, how do I usually explain this? Whoops, okay. Notice that all of these fractions are over 3, okay? So when I do my GCF, it's going to be something over 3. I'm going to throw that into the GCF. And that numerator is just going to be the GCF of the other numerators 1, 2, 4, and 1. And of course, the GCF of 1, 2, 4, and 1 is just 1. Okay. And then the GCF of x to the 4th, x to the 3rd, x to the 5th, and x is what? It's x, right? Because that's the smallest power of x that you see up there. Okay. So I'm going to factor a 1/3 x out of this. And now I'm going to be a little lazy. I'm not going to rewrite it inside the thought bubble. I'm just going to think, okay, what happens when I divide each of these terms by 1/3 x? Well, let's see. So x to the 4th divided by x is x to the 3rd. 1/3 divided by itself is 1, right? 2/3 divided by 1/3 is 2. That's something that you might want to pause the video and think about. So what I'm going to get out of this second term is 2. And then x to the 3rd divided by x is x squared. -4/3 divided by 1/3 is -4. X to the 5th divided by x is x to the 4th. And then 1/3 x divided by 1/3 x is 1. Okay. So that's what I have if I were to divide each of those terms by 1/3 x. So the answer to my factoring problem is that that's one of the factors, and the other factor is 1/3 x. Okay, so hopefully that doesn't seem as scary as it might have at the beginning. All right, so what's going to happen next is we're going to warm up for the last thing that happens in this section, which is factoring by grouping. All right, so this looks a little different. We have z times y plus 4 minus 3 times y plus 4. Remember, factor means write the entire thing as a multiplication problem. This has multiplication in it, but it is actually a subtraction problem. The main operation in this problem is subtraction. All right, so the way I like to deal with a problem like this at first is to pretend that instead of saying z times y plus 4 minus 3 times y plus 4, it just says, sorry, trying to juggle my different colors here, zx minus 3x. So if that was the problem, that would be easy. The GCF would be x, right? And then the other factor that's left would be z minus 3, right? Well, this is basically the same problem. It's just that we have y plus 4 standing in for x. So I'm going to treat the y plus 4 as my GCF, and we usually write the GCF out front. And if you do your thought bubble, you know, picture, I'll do it in yellow this time because that's a little, I'm trying to wean you off the thought bubble. Just picture what would happen if you divided out the y plus 4. You would be left with z minus 3, right? Just like we had in the other problem. Okay, now for this one, I think I will talk a little bit about the check. So I'm saying that this is the final answer. You want to be careful how you check this one. So when you multiply binomials together, it's likely that you were taught to use FOIL, right? First, outer, inner, last. That is not the way you want to do this one, all right? The way you want to do this one, and when I used to teach beginning algebra, I would make my students suffer for about 30 minutes through doing it the sort of more official way, which is to distribute one of the binomials into the other binomial. So this is what we're calling the check. I'm going to take my y plus 4 times z minus 3. I am going to distribute the y plus 4 here and here. And what that gives me is z times y plus 4 minus 3 times y plus 4. Now, if you were multiplying these binomials together, you would continue with distributing the z and the minus 3. Okay, but we're actually going to stop right here because that is my original problem. All right, and the last example for this set is pretty similar to the last one. So the only thing I'll point out that sometimes trips students up, so my GCF is z squared minus 6. So that's going to be part of my answer. Okay, but what's going to go next to it? Well, again, think about your thought bubble. If you were to divide each of these terms by z squared minus 6, you would be left with not only an r from here, but when you cancel these out, it just doesn't all disappear, right? It leaves a 1. Z squared minus 6 divided by z squared minus 6 is 1. So make sure you don't forget to write that 1 there. The other way you can think of it is there is an invisible 1 sitting here, and that's why you need r plus 1 and not just r. Okay. So final answer, z squared minus 6 times r plus 1. All right, almost done. Section 6.1. So now we are ready for actual by group. Factoring by grouping is usually used when a polynomial has 4 terms. So I'm telling you that for x, all right? Sometimes your polynomial is going to have 2 terms, 3 terms. If it has 4 terms, think about grouping. All right, so here are my 3 examples. All right, and again, I'm reminding you, try greatest common factor first. Okay. So switching back to the tablet one last time. Here we go. We have 5x plus 15 plus xy plus 3y. So the first thing I'm going to think about, is there anything that all 4 of those terms have in common? And the answer is no, because, for example, 15 and xy, the middle 2 terms, they don't even have anything in common. Okay, so GCF is no help. Okay, but because it has 4 terms, I'm thinking factor by grouping. So this is how factoring by grouping works. You group the first 2 and the last 2 together, and you see if those pairs of terms have a greatest common factor. And this time that works. I see that I can factor a 5 out of 5x plus 15, and that leaves me 5 times x plus 3, right? And then out of the second 2 terms, I can pull out a y. When I pull out y, and this is really important, what am I left with? I'm left with x plus 3. Again, all right? Notice that those 2 binomial factors are the same, and they need to be the same in order for factoring by grouping to work. So now this problem looks just like the last 2 that we were practicing. My greatest common factor is x plus 3. And when I divide out that x plus 3, I'm left with my other factor is 5 plus y. So this one you can check using FOIL, actual FOIL, first, outer, inner, last. So let's see how that works out. X times 5 is 5x. 3 times 5 is 15. X times y is xy. 3 times y is 3y. Oops, I did that. I actually went FIOL, right? But that worked out because that gave me the same answer that I started with, right? The order of the terms doesn't matter. You know, as long as the signs are attached to the correct terms. Okay, so this was really a, what would you call that? FIOL? It was not FOIL, it was actually first, inner, outer, last, right? Okay, but that worked out. All right, next example, we're almost done. 2x cubed minus x squared minus 10x plus 5. So first thing I look for is a greatest common factor. And again, nothing helpful. For example, 2x to the third and 5 don't have anything in common, so there's no way that all 4 have anything in common. So I'm going to look at pairing the terms up. Okay, and now I have to be careful. That minus in the middle is a little tricky at first. 2x cubed minus x squared. They have an x squared in common. And when I divide out the x squared, I'm left with 2x minus 1. Okay, now notice the second two terms are minus 10x plus 5. Remember what I told you earlier, usually when it starts off with a minus, you're going to factor out a minus. This time I really have to factor out a minus because remember, I need this other binomial to be 2x minus 1. And the only way I'm going to make that happen is if I pull out a negative 5. That has to be a negative 5, right? Negative 5 times 2x is negative 10x. Negative 5 times negative 1 is positive 5. So since those two binomials are a match, that is my greatest common factor, 2x minus 1, and my other factor is x squared minus 5. And don't forget, you can always check that by using either FOIL or FIOL. All right, so that brings us to the very last example for section 6.1. Okay, what did I tell you to always look for first? Greatest common factor. This time we do get something out of the greatest common factor. What do all 4 of those numbers have in common? They're all even, right? Which means I can start this one off by pulling out a 2. So that's going to give me 6x squared y minus 21x squared minus 2y plus 7. And now I'll do the rest of it like I was doing my other problems. Okay, I'm going to have to use 2 different kinds of brackets here to make it a little easier to read. 6x squared y and minus 21x squared, what they have in common is 3x squared, right? And if I were to divide those 2 terms by 3x squared, I would be left with 2y minus 7. So now how am I going to make a 2y minus 7 over here? What would I have to pull out of negative 2y plus 7 in order to get 2y minus 7? Sorry, my nose is a little runny. I do not have COVID. Okay, I need to pull out a negative 1. All right, so hopefully that makes sense. Ignore the 2 for a second, just bring it along for the ride. All right, my common factor is 2y minus 7, and my other factor is 3x squared minus 1. All right, if you wanted to check this one, which I would definitely encourage you to do, I just want to point out something. A lot of students make a mistake with this. If you were to check this, now let's go ahead and check it. You might want to start out by taking that 2 and just distributing it into one of these factors, not into both. Okay. So that would give me 4y minus 14, and now I would multiply that by 3x squared minus 1. And using FOIL, I will try hard to use actual FOIL this time. First would be 12x squared y. Outer would be minus 4y. Inner would be minus 42. Sorry, I really have to cram this in here. X squared, and then plus 14, which is the same thing as what I started with, except for the order of the middle terms, right? So that's the same thing. I'm not even going to bother rewriting it. That checks out. And that's going to do it for section 6.1. So we'll see you next time. We will start talking about factoring trinomials. Take care.